Okay, let's jump into something really, well, mind-bending in physics. A concept that truly bothered one of the greats.
I mean, Einstein.
Exactly. Imagine particles linked together in some mysterious way, so linked that measuring one instantly tells you something about the other, no matter how far apart they are.
Yeah, that's the core idea, and Einstein famously called it spooky action at a distance. He really disliked it. He thought it pointed to a flaw in quantum mechanics.
But here's the twist. This spooky thing, quantum entanglement, it's real. It's been proven. So much so that the 2022 Nobel Prize in Physics went to the scientists who did the key experiments verifying it.
Right. Alain Aspect, John Clauser, and Anton Zeilinger, their work was groundbreaking.
Totally. And for this deep dive, we're actually going straight to their Nobel lectures. We're pulling out the key explanations directly from them.
So our plan today is to unpack this whole story for you. We'll look at where Einstein's unease came from, then how John Stewart Bell turned it into a testable question.
And then, crucially, the experiments by Aspect, Clauser, and Zeilinger that showed this quantum weirdness is how reality actually works.
And finally, why this matters today, how this strangeness is actually, fueling new technologies.
We've got quite the cast. Einstein, Bohr, Schrödinger, Bell, and our three laureates. It's going to be a fascinating trip into, well, the foundations of reality.
Definitely. So let's rewind a bit. Back to the early days of quantum mechanics, maybe the 1920s, 1930s.
Okay, so quantum mechanics was working incredibly well, making predictions that matched experiments perfectly. But Einstein had a problem with it.
He accepted the calculations worked, but he wasn't comfortable with the inherent probability, the randomness. He believed there had to be a deeper level.
Like hidden information.
Exactly. Hidden variables, he called them. Variables that determined the outcome of any measurement beforehand. We just didn't know them. So things weren't truly random, just appeared that way because our theory was incomplete.
And this led to the famous EPR paper in 1935. Einstein, Podolsky, and Rosen.
Precisely. They cooked up this thought experiment. Imagine you create two particles. Let's use photons, particles of light, as the laureates often did.
And these photons are linked in a special quantum way, then sent flying off in opposite directions.
Right. And you can measure properties of these photons, like polarization. Think of it like using sunglasses, a polarizer, to see if the light wave is oriented vertically or horizontally. You get a result, say, +1 for vertical, -1 for horizontal.
Okay, but what's the special link?
That's entanglement. The EPR paper described a state where the two photons are described by a single mathematical object, a shared state. You can't describe photon A independently of photon B.
So they're not just two separate things anymore.
Not in the classical sense, no. Aspect described it as a state that cannot be factorized. Their properties are tied together, like Schrödinger's cat, but for two particles. Before you measure, neither photon has a definite polarization, but their potential polarizations are perfectly correlated.
And the prediction was perfect correlation.
Exactly. If you set up your polarizers in the same direction, say vertically, and measure photon 1 and get +1.
You know, photon 2 will also give +1 if measured vertically.
Yes.
100% certainty.
Yes. No matter how far apart they are, millimeters or light years.
Wow.
And this connects to what physicists call the projection postulate, or state reduction. Measuring photon 1 seems to instantly fix the state or the reality of photon 2.
And that's the spooky action at a distance Einstein hated.
Precisely. How could measuring here instantly affect something over there? It seemed to violate his principle of local reality, the idea that influences can't travel faster than light.
So for him, this correlation wasn't spooky influence. It was proof that the properties were already set from the start by those hidden variables. Quantum mechanics was just missing them.
Right. And for a long time, it stayed mostly in the realm of, well, philosophical debate. Einstein versus Bohr, locality versus completeness.
Until John Stewart Bell came along in the 1960s.
Ah, Bell.
Yeah.
Yes. He did something incredibly clever. He took Einstein's idea of hidden variables seriously. Let's assume they exist, he said.
Okay. But he added a crucial condition. These hidden variables must be local. What happens here, the result of measuring photon 1, cannot depend on what setting you choose for the measurement, way over there on photon 2 at that instant, and vice versa. Only local influence is allowed.
That sounds reasonable. It fits with Einstein's view.
It does. But Bell then proved something remarkable mathematically, his theorem. He showed that no theory based on these local hidden variables could reproduce all the statistical correlations predicted by quantum mechanics for entangled particles.
Wait, so local hidden variables predict different correlations than quantum mechanics?
In certain situations, yes. Bell derives an inequality, a mathematical rule that sets a limit on the strength of correlations you can get if local hidden variables are true. Think of it as a score. Local hidden variable theories predict the score must be, say, less than or equal to 2.
Okay, a limit based on local realism. Exactly. But quantum mechanics predicted that for specific angles between the polarizer settings, the correlations would be stronger. The quantum score would be higher than 2, specifically 2 times the square root of 2, which is about 2.8.
So a clear conflict.
A direct, testable conflict. Bell turned a philosophical puzzle into an experimental question. You do the experiment. Do the results obey Bell's inequality, supporting local hidden variables, or do they violate it, supporting quantum mechanics and its non-locality?
The stakes were suddenly very high. It was quantum mechanics versus Einstein's fundamental view of reality.
And Aspect points out how simple Bell's actual proof is, like a high school exercise calculating averages, yet the implication is profound.
So the race was on to actually perform these tests.
Indeed. And this brings us to the experimentalists, starting in the 70s with John Clauser.
Right, Clauser was a real pioneer here. He worked with Stuart Friedman initially, then did further experiments. They were among the very first to try and test Bell's ideas in the lab.
They used a variation of Bell's inequality, the CHSH inequality Clauser, Horn, Shimoni, and Holt, which was more practical for real-world experiments that weren't perfect.
What were the challenges back then?
Oh, big challenges. The sources of entangled photons they used, excited calcium or mercury atoms, were quite weak. The detectors weren't great, technology was limited.
But they managed it.
They did. Their results, published in '72 and later, showed a clear violation of the CHSH inequality. The correlations were stronger than local realism allowed, matching quantum mechanics. Clauser mentioned getting results like 6 standard deviations away from the local hidden variable prediction, statistically very significant.
So, early evidence against Einstein's view.
Yes, though there were some initial conflicting results from other groups, Clauser repeated and confirmed his findings. He also did important work confirming photons really act like particles in this context, which was an underlying assumption.
But there was still a potential issue, wasn't there? The locality loophole?
Exactly. In those early tests, the polarizer settings, the angles were fixed before the photons even left the source.
So could there have been some, I don't know, secret communication, some slower-than-light signal arranging the results beforehand?
That was the loophole. Maybe the measurement devices somehow coordinated, respecting the speed of light, to fake the correlations.
And this is what Alain Aspect set out to fix in the early 80s.
Precisely. Aspect's goal, as he described it, was to perform an experiment much closer to Bell's original thought experiment, specifically designed to close that locality loophole.
How did he improve things?
His team developed a much better entangled photon source using lasers to excite calcium atoms' more intense, purer pairs. They also used better detectors and polarizing beam splitters, which let them measure both outcomes, +1 and -1, simultaneously for each photon.
Okay, better source, better detectors. But the key thing was changing the settings, right?
That was the crucial experiment. They introduced fast optical switches that could change the direction of the polarizers while the photons were in flight.
While they were flying from the source to the detectors.
Yes. The switching time was incredibly fast, about 10 nanoseconds. The time it took light to travel between the 2 detector stations was longer, about 20 nanoseconds.
So the choice of measurement setting on one side was made after the photons were separated, and too late for any light speed signal from that choice to reach the other side before its measurement.
Exactly. It directly tested the locality assumption. There was no time for any local, slower-than-light coordination based on the settings.
As a result.
Still a clear violation of Bell's inequality. By about 6 standard deviations matching quantum mechanics, even with the rapidly changing settings, this was huge. It was the first time the dice were thrown, so to speak, at the last possible moment.
Really strong evidence against local hidden variables then.
Very strong. And then Anton Zeilinger and his group took things even further.
Zeilinger came a bit later to entanglement.
Yeah, he mentioned hearing about it in '76 and initially having no idea what it was about. Shows how counterintuitive it is. But his group made massive contributions.
What were their key advances?
A big one was popularizing a new source. parametric down conversion. It creates entangled pairs much more efficiently and cleanly than the atomic sources. This opened the door to many new kinds of experiments, including sending photons down optical fibers.
And they looked beyond just pairs of photons.
Yes, they pushed into multiparticle entanglement, creating states with 3 or more entangled photons, the GHZ states, named after Greenberger, Horn, and Zeilinger.
What was special about those?
Get this. For GHZ states, the predictions of local realism and quantum mechanics aren't just statistically different. For certain measurements, they predict the exact opposite outcome, 0 versus 1. It's an even starker contradiction.
Wow, like a direct, you're wrong.
Pretty much. And Zeilinger emphasized that much of their work wasn't just about testing foundations, it was about building the quantum toolbox. Trying to create GHZ states drove the development of techniques like quantum teleportation.
Transferring a quantum state without moving the particle.
Exactly. And entanglement swapping, creating entanglement between particles that never interacted directly. These became crucial tools for the emerging field of quantum information science.
Zeilinger also did that experiment about delayed choice, right? That sounds particularly weird.
But it is the delayed choice entanglement swapping experiment. They showed that whether 2 photons ended up entangled could depend on a measurement choice made later in time, long after those initial photons had already been detected and their information stored.
So the past reality depended on a future choice.
It certainly challenges our simple notions of cause and effect and when reality becomes definite. Zeilinger often quotes Bohr via John Wheeler. No phenomenon is a phenomenon unless it is an observed phenomenon. The observation seems crucial, maybe even retroactively.
That's a lot to wrap your head around.
Tell me about it. His group also pushed the distances entanglement over tens of kilometers in fiber, over 1,000 kilometers via satellite. And they did these amazing experiments using light from ancient quasars or the cosmic microwave background billions of years ago to choose the measurement settings.
Why do that?
To rule out any possibility of some vast cosmic conspiracy, some hidden variable signal coordinating everything since the Big Bang. If even choices determined by causally disconnected parts of the universe still yield quantum correlations, it makes local realism even harder to maintain.
They even use people making choices.
Yeah, the Big Bell test or human choice experiment. Thousands of people worldwide generated random numbers that controlled the settings in real-time Bell experiments. It was partly a nod to Bell's own musings about whether human free will could be the ultimate random choice generator needed.
So after all these increasingly sophisticated experiments,
By around 2015, several groups, including Zeilinger's, managed to perform loophole-free Bell tests. These experiments simultaneously close the locality loophole and other potential loopholes related to detector efficiency, ensuring the observed violation wasn't an artifact of the setup.
the verdict was
Pretty definitively. The experiments consistently violate Bell's inequality and agree with quantum mechanics. As Clauser bluntly stated, invoking Star Trek, local realism is dead, Jim.
okay, so if local realism is dead, what does that mean? We have to accept non-locality.
That seems to be the consequence the experiments force on us. We have to accept that quantum mechanics involves these non-local connections.
And what Einstein saw as a bug, a spooky problem.
Is now seen as a feature, a resource. That's what Aspect emphasized. This non-locality is the foundation for quantum information science and a whole new generation of quantum technologies.
Right. Let's talk applications. Quantum cryptography comes up a lot.
It's a major one. The goal is secure communication, often boiling down to sharing a secret key between 2 parties, Alice and Bob, without anyone eavesdropping.
How does entanglement help?
Alice and Bob share entangled pairs. They each measure their photon randomly, say choosing between vertical, horizontal, or diagonal settings. When they happen to choose the same setting direction, quantum mechanics guarantees they get the exact same random result, +1 or -1.
So they build up a shared random string of bits.
Exactly, a perfectly secret key, like a one-time pad, the only provably secure classical cipher.
And why is it secure? Where does non-locality come in?
Because the result isn't determined until the measurement. There's no pre-existing information traveling with the photon for an eavesdropper, Eve, to intercept. If Eve tries to measure a photon in transit, she inevitably disturbs the delicate entanglement.
And Alice and Bob would notice.
Yes. They can sacrifice some of their measured bits, communicate openly about the settings they used and the results they got for those bits, and check if the correlations are still perfect. If Eve was listening, the correlations will be messed up. They'll detect her. Zeilinger's group famously sent an image of the Venus of Willendorf this way.
Very cool. What else? Quantum computing.
Absolutely central. Entanglement is a key resource needed to build powerful quantum computers. Those GHZ states, for instance, are a type of entangled state relevant to quantum algorithms. It allows quantum computers to explore vastly more possibilities simultaneously than classical ones.
So we need entanglement for the quantum future.
Definitely. And things like entanglement swapping are crucial for building quantum networks, a future quantum internet connecting these quantum computers. Plus, quantum effects are used for ultra-precise measurements.
It's amazing that these technologies are emerging from something so fundamentally weird.
It really is, and it forces us back to those deep philosophical questions. Violating Bell's inequality means giving up something intuitive. Usually, it's seen as giving up local realism, the combination of locality, and the idea that properties exist before measurement.
Zeilinger had some thoughts on this.
He wondered if maybe our strict separation between physical reality and the information we have about it is the problem. Perhaps they're more unified than we think.
But Clauser, even after winning the prize for proving it, still expressed some confusion.
Yeah, it's fascinating. He talked about the two ways physicists visualize quantum mechanics. School one, single particles, waves spreading in our normal 3D lab space. He argues this view is actually a kind of local realism, and his experiments killed it.
Okay, what's school two?
That's the one needed for entanglement. It describes the system using a wave function in a highly abstract mathematical space configuration space, which has many dimensions, one set for each particle. This works mathematically, but Clauser admits he has no idea how to intuitively picture things propagating or what reality looks like in this abstract space.
So he sees a disconnect between the math that works and our physical intuition.
A deep disconnect. He calls it Born's ambiguity, stemming from how we interpret the wave function. How can these two different mathematical descriptions, lab space versus configuration space, possibly describe the same underlying reality? He finds it baffling.
And he even threw out a challenge connecting it to gravity.
Right, a provocative question. Can you even have two entangled black holes? Since general relativity, which describes black holes, is built on a local realism framework, how does that mesh with the proven non-locality of entanglement? It highlights a fundamental tension between our best theories.
Wow, so what a journey. From Einstein's worried thought experiment
To Bell's brilliant theoretical challenge.
and then these incredibly careful decades-long experiments by Clauser, Aspect, Zeilinger, and many others, nailing down the reality of entanglement and non-locality.
And showing it's not just some weird footnote in physics, but the key to potentially revolutionary technologies.
Yet, the laureates themselves remind us that fundamental questions remain. We've proven quantum mechanics works, but fully grasping what it means for reality, that's still ongoing.
It makes you wonder, doesn't it? Is this entanglement a sign of some deeper, hidden connection weaving through the universe? Something fundamentally linking events across space and maybe even time?
And how seriously should we take results like the delayed choice experiment? Does our observation really play such an active, maybe even retroactive role in defining reality?
Or wrestling with Clauser's confusion. Are we stuck with mathematical descriptions that work but defy our intuition about physical space? How do we bridge that gap to truly understand the quantum world? It feels like, despite the Nobel Prize, the deepest quantum mysteries are still unfolding.